Okay, we're recording, guys. All right, so how's everyone doing this morning? You can unmute if you want. Everyone thumbs up from... Okay, all right. Well, I'm going to share my screen to lecture 4. Share, okay. And let's see here. Let's see if I can make this a little bit bigger so you guys can see it. How's that? You guys see that okay? Somebody give me a thumbs up? Okay, great. Okay, so today is lecture 4, and we're going to start where we start all our lectures, right here. Okay, in order to get the most efficient design, the most structurally optimized frame or monocoque or whatever, you need to be concerned with both geometry and materials. Okay. So, having said that, how many of you guys, and you can unmute if you want, how many of you guys watched Battery Day, Tesla Battery Day? Anyone? Guys, unmute. Go ahead. Anyone watch this?
But it's only like halfway up.
I read a little bit of a summary.
A little bit of summary? Okay. Well, so there was actually a fair amount of discussion about structural optimization and materials during the shareholder meeting, during Battery Day, which was actually quite nice to hear. It turns out actually that the head of materials engineering at Tesla is a former student of Greg Olson's. So Greg Olson is now a professor in your department, the material science department. And if you remember, there was a discussion about large castings. Did anybody hear this part? So there was a big discussion about large castings. You know, typically when the way that's kind of a traditional way for the auto industry to make a body structure for a car, for a production car, not a racing car, but a production car, is they make a lot of steel stampings, many steel stampings. I think like the Chrysler, if I remember correctly, has around 300 different stampings in the body structure. The Mercedes has about 600 different stampings in the body structure. Each of those parts, you have to keep track of tooling, and you have to do dimensional checks on each part, and you have to have a separate quality control person for each part. So it's a tremendous effort to keep track of every part. Not to mention you have weight that's tied up in the seams where you join these parts together. So by combining lots and lots of parts into a single casting, you can not only reduce the amount of money you're spending in some cases, but also you can reduce weight very, very substantially. So the strategy to make big castings has been around for at least 20 years that I know of. And there was some work back at Chrysler back in the early 2000s with Alcoa. And it's really, there's been some big castings in from the Ferraris and more recently the new Corvette and Audi A8. But it is picking this up. And he actually discussed a little bit too about the alloy. And he talked about having a special alloy that would not require heat treating. So you have a big molded part like this, you heat it up, and you're bound to get some distortion when you heat treat it. So you don't want to have to heat treat these parts because it'd be impossible to control them dimensionally. But at the same time, the material has to have some alloy content in order to get it to fill the mold properly. You have to reduce the fluidity, reduce the viscosity of the aluminum so that it'll completely fill the mold. There's a real challenge there, and Tesla developed their own alloy to do this, and they did it using these kind of methods similar methods to what I showed you on the second day when we talked about strengthening materials. They used this, the latest in what's called Integrated Computed Materials Engineering, ICME. And you guys heard about that? Give me a thumbs up if you had. Integrated Compute, ICME. Anyway, this is a big topic in metallurgy and a couple other material science topics right now. It's part of the National Genome Materials Initiative started by Barack Obama. So it's really encouraging to see this. Now, I would say that in the design that Elon Musk used, there is, from a structural engineering perspective or structural optimization perspective, there actually really is, I think, something here that at least I'll call it controversial. Now, I don't mean to poke fun at Elon Musk or criticize him or his engineers or what they're doing. I'm a huge fan of Elon Musk. I'm a huge fan of Tesla. But nothing's perfect, and there's probably a good reason they did it. But I'll just show you this little design flaw right here. So this casting takes up the rear part of the vehicle, the kind of rear wheelhouses and the rear floor pan. And there's these webs that you can see in this picture here and here. This is the same part. That web right here is actually located at the side of the rear rail, like we discussed body components and beams last time. So right in here. Okay, so I'm going to ask you guys to unmute. Everyone unmute. Go ahead. Go ahead, unmute. Come on, guys. Andrew, can you unmute?
Yes.
Okay. Okay, everybody unmute. Can you guys see, given what I discussed last week about how beams are loaded, can you see the design flaw here? Can you see the compromise that was necessary to make, probably to make this thing castable, that they've created here? You see the mistake? I'll give you a couple seconds to think about it. Okay. Anyone want to venture a guess?
I mean, I guess it's not like a completely closed member.
Exactly.
Like a
Exactly. So this part, now again, this isn't like a heavy criticism of Tesla or anyone there. I'm sure there's a good reason they did this. I'm sure they were sort of, maybe the design of getting it out of this big mold, they had to do this. They had no other choice. But there is a design compromise associated with doing this. And if you think about the whole body structure under a torsion load, okay, and remember we talked about a beam and torsion, right? And we talked about how the stress is highest at the outside surface of that tube or that cylinder in torsion. And then you think about this area that's open. It's open to the material that they removed in order to make this, I'm guessing in order to make this part castable, was in the highest stressed area of that part when the body's under torsion loading. Okay, so they have all that extra stress concentration created, and they've lost that opportunity to reduce weight and maximize stiffness. So I just wanted you guys, it's like I said, it's not I'm being critical of Tesla or Elon Musk or anyone there. It's nothing like that. It's a design compromise, and every compromise has these trade-offs. And I just want you guys to get used to looking at a structure and being critical about what could have been a compromise here, what maybe could have gone better. And this is, because that will help you in the future design better structures. So just looking and thinking about this right here, like this is a design compromise they made. Okay, any questions about that? Another topic that Elon Musk discussed, which I thought was interesting, was the floor pan. So they're going to use the battery cells as structure to support the bottom of the vehicle, the floor pan effectively. So the battery's on the bottom of the car, and there's some skin on the bottom of the car, okay? And then if it's going to be some type of structure, some type of sandwich structure, they'll have like two panels separated by some distance. Okay, that's sort of like if you guys maybe seen a carbon fiber honeycomb panel. So the honeycomb separates the skins of two pieces of carbon fiber and makes that panel stiffer. It makes that panel stiffer using the laws of bending that we discussed last time, where the stress goes down with the cube of the height of the piece in bending, of the beam in bending, or in this case a panel in bending. And he's going to use the battery structure, the steel cans that make the batteries, in order to separate out those floor skins, so that the part will be stiffer and lighter. And I think, he brought up a really interesting example. He talked about airplane wings and how airplane wings are originally held the fuel, the kerosene or gasoline, whatever they run on, inside a tank inside the wing. And then somebody said, well, maybe we're using too much double structure there. So they combined the skins of the wing with the fuel tank, and they created a stiffer, lighter structure. So that's pretty common in airplanes now. And in fact, I think it's pervasive in airplanes. So this is a similar idea. But it's really, I tell you, it was really, really impressive to me that the CEO of a car company would understand that sort of thing, because I can tell you from my experience that the CEOs that I've known from from car companies are usually very, 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 very far removed from anything quite that related to structural optimization. So I was very impressed by the battery day. I know their stock. I don't know if you guys have been watching. Their stock got absolutely hammered, like it's down like 20% like 3 days ago. But anyway, I was very impressed. Okay, next, let's start here. So I want to introduce you to Lucian Schmidt. Lucian Schmidt, I think, is considered the father of structural optimization. He may have called it structural synthesis in some cases, but he really is the father of structural optimization. He was a student at your fine institute back in the 40s. He got a BS and an MS, I think, in aerospace engineering. He worked at Grumman Aerospace for a couple years, and then he went back to MIT to be a professor. Case Institute, which is now called Case Western Reserve, lured him away to be a professor for a while there, and then he moved on to California to go to University of California, Los Angeles. And he was a professor there until 93. He retired in 93, and he just fortunately passed away in 2018. But he is really the first guy to ever look at these structural engineering problems that we're talking about in a very systematic way. And the first time that anyone ever proposed the idea of using this systematic approach. The systematic approach is called numerical optimization. Using numerical optimization in conjunction with finite element analysis to optimize structures. He was the first guy to ever propose that. And that's the tools that came out of that approach are pervasive now. Pretty much every car manufacturer, any supplier who's involved with making components that need to be lightweight uses this approach. Uses these tools. They use this numerical optimization codes that are attached to finite element codes, and the tools they use are we'll get into them later. We'll talk about them in detail, but they're topology optimization and topometry optimization, topography optimization, shape optimization. These are all methods and tools that came out of the work that he did that are now very popular and used on airplanes, cars, motorcycles, bicycles, all kinds of places where lightweight and stiff is important. So the reason I'm giving you, by the way, the name of some of these professors and engineers and scientists in the field of structural optimization is my hope is that you'll go to your library, or at least go to your library virtually now, and type in their name and the author is an author and see what comes up, and maybe find some papers that you think are interesting and read through them. Because I've got a whole stack of them. I've really, over the years, have keep going back to them and referencing them, and they're all very interesting. Right, so here is an example from one of Lucian Schmidt's papers. This is the paper was actually, I read was 1981, but I think this actual problem was solved like in the 50s. So suppose you have a thin tube, hollow tube, okay, thin wall, T, that's under a compressive load, like you see right here on the left. The length of the tube is L, the diameter is D, D2, the inner diameter is D1, the thickness of the wall is T. Okay? This thing is under some load, this compressive load, because it is narrow, it has this high aspect ratio of diameter to length. It's subject to buckling failure mode, okay? So there's sort of Euler buckling, which is when the whole thing sort of goes wiggly, call it, at some load. It's sort of a global failure, and then there's sort of a local failure mode, which is a local instability of the surface that causes local buckling. And if you had a solid tube under the same loading condition, you would only really have to worry about Euler buckling. But because it's hollow, you got to worry about local buckling too. So your job as an engineer is you can't change L's fixed. You can change the diameter, the outer diameter, and you can change the thickness T. So you have two design variables you can play with in order to find the lightest structural tube in this application that can support this load P, as in Paul. The weight of this tube is very readily calculated using this equation on the top. So the density of the material times pi times the length times the outer diameter of the tube D times the thickness of the wall T. Okay, if you plot out, I'm trying to move over the screen so I can see this now. If you plot out on a graph thickness versus d, the diameter of the tube. Okay, you can plot iso weight lines on this graph. Okay, and those are W. Okay, so you guys see my cursor? Can you see I'm pointing out the dimension T here and then pointing out the dimension D? Okay, thank you, Mr. Bang. Thickness and diameter in inches, okay? These lines, these W lines, these are iso weight lines, okay? As you go from the upper right to the lower left on this graph, you're going lower and lower in weight, okay? As you go up this way, you're gaining in weight, obviously. There are certain constraints that your boss gave you, because maybe they got to package this tube somewhere, maybe it's the, certain diameters they can get under a certain number, cost less money, whatever. You've got certain constraints that you have to follow, okay, to find that lightest weight solution. So the constraints are the diameter of this tube has to be less than 4. Okay, the maximum allowable diameter is 4 inches. Okay, so if we plotted that on this graph, we would get this vertical line right here at 4 inches. Okay, D equals 4 inches. That's the equation. D equals 4 inches right here. That's line. So you know that you can't be to the right of this line, because that would be outside your allowed constraints. In fact, you have to be to the left of this line for this to be a feasible design. Okay, you're also told that the thickness of the tube, okay, the wall thickness has to be greater than 20 thousandths of an inch. So that line at 20 thousandths of an inch is given by this gray line underneath the red line right here. I don't know if you can see that. There's a line right here. So you can't be below that line, because then you'd be outside your constraints. You have to be above that line. Okay, so now you're sort of in this region that I'm going to outline with my cursor. Okay, your feasible designs are within this sort of loop right here. Okay. The next constraint is the criteria for Euler buckling. This material, you can't go above a certain stress, okay? The critical stress, sigma sub C, okay? If you take sigma, okay, so the stress in the tube minus this critical stress, you say that has to be greater than 0, because then you're always outside of the critical stress, okay? And that gives you this line G1. Okay, so here's G1. That's the line that denotes Euler buckling, and you have to be to the right of this line in order for the stress to be low enough that you're inside your constraints. And then for local buckling, you take a similar approach. The equation's given here, and that's this red line here that kind of makes this kind of jump and then bump and then goes flat. You have to be above that line in order for the cross-section to be big enough that the stress is low enough that you're within your constraints. Okay, and that means that if you look at these lines for W, you look at the lowest iso weight contour that goes through your feasible design space, which is this kind of thing right here, right? I'm outlining it with my cursor. The lowest W that goes through there is right here at this vertex. So that's the lowest weight solution right there. Okay, so somewhere right about 4 inches in diameter and right about 20 thousandths thick wall, given a constant L. That's what's going to give you the lightest solution when you're in this feasible region right here. Okay, so this is a simplification of an approach that will get into more, that will become more and more complex as we go further and further with this lecture, or next lecture and the one after that. But you can see here that you have I want you to start thinking in this terms. I want you to say to yourself, what is the design space? Okay, your design space, you've got a 2-variable design space here. You've got thickness and you've got diameter. Those are the 2 variables that you have to control in order to get to your lightest weight solution. Okay, you guys got any questions about this? This is kind of the foundation, I think, for some things that are going to get much more complicated in the future in this lecture and the next lecture. Okay, Andrew, I see you're shaking your head. That's good. Thumbs up, everybody. Got this? Okay. I'm going to go to a little bit more complex example next. Okay, this is the famous three structural member indeterminate design problem. Also came from one of Lucian Schmidt's papers. Again, the paper I read where I learned about this was printed in 81, but that was probably, I mean, I didn't read it in 81, but it was made in 81. It was published in 81. It was probably this actual work I think was actually done in the 50s. So this is, you know, keep in mind, this is a time before they had computers strong enough to do any kind of series finite element analysis, and, you know, pretty much everything was by hand. So, okay, so in this example, we've got 3 structural members. Okay, they have cross sections A1, A2, and A3. These struts, these structural members are oriented at 45 degrees with respect to the vertical. Okay, so that's 45 degrees. So A1 is 45 degrees to A2, A2 is 45 degrees to A3. You have some fixed distance between where they're attached to some, I don't know, call it the roof of the house, and where they're hanging down below. And then you apply 2 loads simultaneously. Or sorry, you apply, let me take that back. You apply one load condition P1, one load condition P2, okay, of 20,000, what is that, kips? Oh God, this is English units, kilopounds or something. You guys can probably look this up. In order to simplify this problem, we're going to assume that the cross-section of A1 equals the cross-section of A3. Okay? The weight of this structure, assuming those, you know, same diameters A1 and A3, is given by this equation W right here. Okay, it's a pretty straightforward equation. You guys, you know, could derive that kind of thing in your sleep. No big deal. If you consider the design space is A2 and A1. You can only mess with the cross-sectional areas of A1 and A2 in order to find the lightest design. The constant weight contours normalize to the density of the material and the norm, and that distance n, okay, is given by these black lines, these straight black lines. Again, as you go from the upper right to the lower left, weight goes down. You go the opposite direction, weight goes up. So you want to find a design that's as close as you can to the bottom left side of this. Okay. You have some constraints. The material can only handle so much load. And so you need to keep the stress below a certain level. Given the material that you're using, the tensile stress needs to be below 20,000 KSI. Okay, and the compressive stress needs to be above 15,000 PSI, or it's because it's negative, we're called negative 15,000 KS, or 15 KSI, right? So your stress, this is the maximum stress that this material can take, has to be between these two levels. So the stress sigma I comma j is defined as I being the stress in the ith member at the jth loading condition. So in this case, the jth loading condition is P1. Okay, and then this is 1, 2, 3. So the I is 1, 2, 3. So the stress in each of those members, given that loading condition, these 3 equations. Okay, the constraints are defined by these 3 equations right over here. And so you need to keep, again, you need to keep the stress in member 1 under the first loading condition. This subtraction, you need to keep this greater than 0 so it doesn't go above 20,000. Same thing here, and then here you need to keep it above 15,000, negative 15,000. So these are your constraints, okay? H1, H2, and H3. Now, if I went ahead and plotted H1, H2, and H3 on the graph, you get these blue, green, and red lines you see here. So H1 is given by the blue line. Okay, that's H1 equals 0. H3 or H2 is given by this red line, and H3 is given by this green line right here. So those are when that's the absolute maximum. Those lines are the absolute maximum you can push the stress. Sigma 1, 1, sigma 2, 1, sigma 3, 1. Okay, so for the for H1, so this like I said, this is what these equations, this is when these equations equal 0. What these are the different combinations of A1 and A2 you can put in to make those equations equal to 0 for H1, H2, and H3, given by those lines. So for H1, you need to be this side, right, in the feasible region. For H2, you need to be above this red line, so you're up here. And for H3, again, you need to be the right of the green line. Taking the sort of the sum of all those different constraints, the feasible region is given by what I'm going to trace out. So it's where my cursor is down to 0.3, down to 0.1, down to 0.2, over here, up and over. So, and to here, not to the blue line, to the green line. So you've got, this is the feasible region. These are the designs that you can pick that stay within your constraints for stress. So given that the weight lines, these are the constant ISO weight lines, right? These are the constant weight lines, these black lines. You're going lighter as you go towards the bottom left. The lowest ISO weight line that you can touch is at 0.1. See right there? That's the latest design you can get. That's 2.64 pounds. A1 and A3 equal 0.7 inches squared. That's the cross-sectional area. And then A2 is 0.41 inches. That's the cross-sectional area for 2, which is right here, A2. So there's something interesting about this design. I think if you take a lot of engineers and you say to them, okay, how can I make this thing as light as possible? They're going to say, oh, well, just figure out the stress in each one of those beams and then go to the minimum cross section that supports that stress. And maybe, in the real world, you put on some type of safety factor for anything that's not understood, or defects in the material, or some screw up in the supply procurement department. Okay, and that should give you the lightest solution. It turns out, in reality, so they call that type of solution where you just go to the minimum cross section and everything. They call that solution the simultaneous failure criteria, also known as fully stressed design. And what's interesting is that it actually, in this case, didn't actually give you the lightest design. If you look at 0.2 right here, which is that simultaneous failure criteria right here, and you look at 0.1, 0.1 is actually on a lower ISO weight line. So even though one of the materials was maybe a little bit above its completely stressed limit, you actually had a lighter design. So don't assume that you could just always go to the, make everything as thin as you can and that'll be the right way to design. It doesn't always work that way. And I can tell you from experience. One time when I was a body engineer at Chrysler, we were working on making the body structure for the Chrysler Sebring. Car wasn't very successful, wasn't really competitive, but there was a point there where we were trying to optimize the thickness of every body panel, which was stamped from steel. And we did what's called the multidisciplinary optimization, where we used finite element analysis under a variety of different loading conditions, impact and torsional and bending stiffness, maybe 11 different loading cases. And it actually turned out that we could get a lighter solution by thickening some panels and thinning some panels. So making some panels thicker than they needed to be, even based on the stress that they were handling. So the fully stressed design, the simultaneous failure criteria, is not always going to be the lightest design. I want you to remember that. Any questions on this example? Good? We're good? Okay. Okay, so oops. Again, you've just been given the concept of a multi-dimensional design space. Okay. In abstract, what we've done is shown in this graph here. Okay, this cartoon here. This is let's call it a ski resort. Okay, this is a mountain on a ski resort with some snow fences. The objective is to get to the top of the mountain. So you want to maximize this function f. But there's certain constraints. You've got these snow fences. You can't go skiing beyond the snow fences. So you've got these constraints. Call them g and h. Those are the functions that describe the constraints for where you can go and where you can't go. And that's just like this. It's the same thing as this, except we're just, rather than being real concrete with examples of diameter or thicknesses, we're going to be a little abstract. We're just going to call these some abstract constraint, g and h. Suppose you're at the bottom of this hill and somebody blindfolds you and they say, okay, get to the top of the hill. You're blindfolded, you can't see, You don't know where the top of the hill is, but you got to go to the top of the hill. That's your goal. So you start at this point here where it says start, and then you take a couple steps. You go from this F to this F, and you think, okay, I have an altimeter on me. I'm a little bit higher, so I know that was the right direction. So I'm going to go that direction again. So you go to here, and you say, oh, okay, my altimeter says I've made it up the hill a little bit further. That's good. And then you try to go a little bit further in that direction, but you hit the snow fence. That's the constraint. So you say, let's try another direction. I'll just turn, 180 degrees or something, and not 180, I'll turn 140 degrees, and I'll head a direction, see what happens. So you do that. And you go from here to here, and you go, oh, gee, I made it a little bit further up the hill. This is good. This is good. So I gained a little bit of altitude. I'll go that direction again. You go that direction again. You get to here. Okay, I'm still further up. This is good. I'll head that direction a little bit further. But then you hit the constraint, and so forth, until you finally make your way all the way up this hill. Okay, this is called numerical optimization theory. How do you get to the top or the minimum of a function if you don't know what it really looks like? I've shown this in a way that discusses hitting a maximum, but it also works for hitting a minimum. Just as we did when we were trying to reduce the weight of a structure, you're finding a minimum rather than a maximum. So you can go down into this valley or down into a crevasse or whatever it is, and you can do the same exact thing. You've got some objective function E. Okay, E is a function of D1 and D2, your design variables, and you're going down, 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 down into this crevasse or hole or valley or whatever it is, and you're hitting back and forth on the fences until finally you start stepping around and you realize you're not getting any lower. You've converged, as they say. That's the word you hear a lot in structural optimization, conversion. You've converged on a minimum or maximum. Okay, so I'm going to require everybody to unmute their phone right now because we're going to play a little game. This is a fun game. Classes I've taught in the past, I usually enjoy this. Okay, so everybody unmute. Okay? So here we have a two-dimensional design space, x1 and x2, right? And the equation for the function or the hill or the curve underneath this design space of x1 and x2 is given by this equation f of x. That's a big complicated equation. I just made that up out of my head. It's nothing special. I made it up out of my head. I plotted it out in Excel. From doing that, I know where the minimum is given this design space, where x2 can go from negative 0.8 to positive 0.8, and x1 can go from negative 1 to negative 0.1. So somebody pick a point, someplace to start in this design space. And these are little blue boxes that I'm going to delete off. So somebody pick a point.
Minus 0.5, comma, minus 0.5.
So right about here, is that the spot?
Yeah.
Delete that. Okay, you got 11.9. I can tell you that's not the minimum. You want to minimize this function. You want to find the minimum of f of x. What do you do next?
Go right.
You want to go right? So this way? This one right here? You like that one? Okay. Guys, as I'm doing this, I want you to very carefully think about what you're doing. Very carefully think about what you're doing and notice what other people are doing and notice what the strategy becomes. What direction you go, how far you go, and what happens to the value of the function. Okay, so just watch very carefully what happens. So I'm going to delete this one right now. And you got 10.3, so you went down. What do you want to do next?
Keep going right.
Want to keep going right? So here, you want to get rid of that one? Okay, you got 9.2, so you're still headed in the right direction. What next?
Mm-hmm. Keep going.
Keep going, okay. So notice the step length. The step length is one box. We're doing a step length of one box, right? The value is 8.4, you're still going down. What next?
Go right, but 4 boxes.
So 1, 2, 3, 4. You like this one right here?
Mm-hmm.
Okay. 7.56. You went down a little bit, but not as much as you had previously. What next?
Go in the middle of the 3 that we haven't undone.
Right here?
Yeah.
That guy right there? Okay. 7.5. So he went down a tiny little bit. What next?
Uh,
Go up by 3 boxes.
From here?
From 7.5, yeah.
So Fiona, you want to go right here?
Mm-hmm.
Okay. Oh, went back up. So that's 11.4. So, you know, that wasn't the right direction.
Go down by 3 boxes from 7.5.
To here?
Yep.
Right here, Andrew? You like this one? Okay. 5.4. Ooh, that's good. You think that's it? Or you think you can go back? You think you can get down further?
maybe,
Down one more.
yeah.
You want to go right here?
Yeah.
Okay. 5.1. So you went down a little bit further.
And now I think we have to check the adjacent ones to 5.1.
So this one and this one?
Yeah.
Okay. That's 5.3. You know, that's the wrong direction. That's 4.93. Ooh, you went even lower.
Ooh.
Jump 2 more to the right from 4.3.
Right here?
Yeah.
4.85. So you're even lower.
Go all the way to the bottom right corner.
Right here? Right there?
Yeah.
Ooh, you went back up.
What about the one that's at 0.6 on X2? Still on the bottom.
Right here?
Yeah.
That guy? Still higher.
I would say 0.4, then try that one right there. Do your 4.
Here?
Yeah.
Nope.
Okay.
Higher still.
Now check 0.02, or yeah, 0.2.
Okay, so that's the minimum.
Okay.
4.84 is the minimum within this domain of that function. Okay, so that was very interesting. Okay, you guys, you know, every class eventually finds the solution here. Some find it quicker, some find it slower. But you followed a pattern here. You picked you randomly pick some spot. Every optimization out there, you pick some random spot to start with. There may be some spot that you have some knowledge of. And then you said, okay, well, let's pick a random direction, a random step length, and see what happens next. Okay, and then you went lower. And then you picked another one and you went lower. And you picked another one and you went lower. And then you said, oh, let's take a bigger step. Let's get more aggressive. Let's see if we can find that minimum quicker. So you took a bigger step. Okay, and all this time you don't actually even know what the minimum is. I mean, I know what it is because I wrote it, but you didn't know what it was. So you had to keep, I wouldn't say at random, but you've chosen a search direction and you chose an increment, how far to go to look for it, and eventually you found that minimum. So here's what it looks like with all the blue boxes taken off, and you can see where the minimum is. Okay, it's at that 0.2 and negative 0.1. And this is a subset, obviously, of a bigger domain, a bigger design space for X1 and X2. If you look at the bigger, a bigger area of this, you have this 4 to negative 1 and negative 2 to 2 for X2 and X1. Sorry, take that back. You have negative 1 to 4 for X1. You've got negative 2 to 2 for X2. And this is a bigger domain. And you're looking at this bigger domain, okay, and the minimum is somewhere else. In this case, the minimum is at 1, 1, and the minimum is actually 4 rather than 4.84. So it should become apparent to you at this point that the minimum is not just, it's going to change depending on how big a design space you look at. And the maximum will depend on how big a design space you look at.
In these structural optimization problems, are there situations which create like multiple local minima?
That's a big problem, right? That's a big problem. That's something that happens for sure. And there's at this point there's incredible software that that's used to do numerical optimization, and whether it's structural optimization, or maybe you're, I don't know, optimizing the temperature of some chemical reaction, or you're, I don't know, finding out the virus site that kills the most viruses. You know, there's always the risk of hitting some local minimum rather than a more of a global, more of, not a total global maximum or minimum, but more of a global, right? So what happens is some of these softwares that do what you guys just did, but they do it much quicker, clearly. Once they find a place where they think they've hit some minimum or maximum, they'll sort of jump around at random and then just test out some neighboring points to understand, was I really at a global or was I really at a local minimum or maximum? So it's a very, what you asked is a very pertinent question. It's something that is one of the biggest risks of doing numerical optimization software that's used to do it.
I have a question about this. So I know that for continuous problems where the design variables can be described continuously, there are methods that you can analytically prove will find the max or the min. Do structural optimization problems, are they usually not, are you not able to use those methods here? So you have to use something more heuristic, or?
So the variables typically are continuous. That's a fact. So yeah, that's exactly what happens. There are methods and techniques and mathematics, and I'll show you some in a little bit. It may not, I don't know if we're going to get to it this lecture, but we'll get to it next lecture. There definitely are ways for, they're definitely, these structural optimization softwares definitely use those methods to determine whether they're at a local or global minimum or maximum. So yes, the answer is yes, they do use those. Some of those things are very complicated mathematically, and I may not be the best guy to describe them, but they do exist. And kind of this is kind of the same thing right here. I think we're gonna have to stop. I'm gonna go through this slide right here, and I think we're gonna stop for the day because the next slide is actually quite involved, and I want to reserve that for a time where we can all focus on it carefully. But looking at this problem, I think this is kind of exactly what you're talking about, Fiona. If you have an unconstrained problem, like you have on the left here of f of x with the design variable x, and you want to find a minimum for f of x, the method you take, you guys learned in first year calculus, you take the derivative of this equation and you find the place where the derivative equals 0, and then you take the second derivative at all those places where it equaled 0, and you determine if that second derivative is positive or negative. Okay, if that second derivative is positive, okay, then you were at a minimum within that, that consigns, that this complete, x distance, right? If that derivative was negative, then you were at a maximum. The world changes when you get to a constrained problem like we have on the right here. Okay, you've got this same thing. You've got function f of x, which you're trying to minimize, and you have some design variable x in this design space x. But you have these constraints, g1 and g2. Okay, the way I've done this, the way I've placed g1 and g2, the minimum and maximum are not at points inside those constraints where the derivative will equal to 0. The first derivative will equal to 0. So in this case, you really can't know, where the minimum is. You might at point B, x equals B, you'll find the first derivative equals 0 there, but you're at a local, you're at some local minimum or maximum. You're not at a global or a minimum or maximum that's within the constraints. So this case, when you're under scenario on the right, constrained problems becomes a lot more complicated. And there are scientists and engineers who've spent their entire careers developing algorithms to search constrained design spaces. And the most popular method for searching this type of design space is called a gradient method. Okay, and then there's some other really creative solutions that have come out where people do what's called genetic search, okay, which is sort of like if you have two organisms that breed and you get an offspring, is that offspring doing better or worse than its parents? There's particle swarm, where you are sort of modeling a bunch of bees looking for honey, and there's the golden rule. There's this list goes on probably for several pages, and guys like Lucian Schmidt and guys like Gerrit van der Plots, you'll meet him. I'll give you his biography tomorrow. These are the people some of the people who've spent their careers looking for these algorithms, and And these guys are like race car drivers. They think in terms of what's the fastest way to get to the solution, and they have competitions among each other who can come up with the algorithm that finds the fastest minimum or maximum in some design space. So there's a lot in this area, but okay. So we're at 9:50 right now. Tomorrow, or not tomorrow, next Thursday, I want to go through this example here very carefully. This really is very similar to one of these, or one of these, or any of these optimization problems, except it's a more formal way of looking at this concept that we did when we did our own game. Where we picked a direction and we picked an increment of length to jump, and we're going to go through this next time. Any questions?
Hi, yeah, I had a question on kind of like the limits of this kind of like automated design concerning geometry. So like something like 5 or 6 years ago, Chrysler sponsored a case competition at my undergrad university to design an upright for one of their cars or trucks or something.
A suspension? A suspension component? Yeah.
Yeah.
You go to Lehigh?
Carnegie Mellon.
Carnegie Mellon, okay. Okay, I know. Well, I have a lot of friends at Chrysler who went to Carnegie Mellon, so okay.
Yeah. And so one of the teams did this kind of like organic design approach where they put in whatever the hard points were and ended up getting geometry that ultimately was strongest and also probably would have been prohibitive to manufacture. So are these tools capable of including factors like cost to manufacture or just even ability to manufacture? Or do you have to kind of enforce that as a...
So the quick answer is yes. But let me go into a little bit more detail. Josh, who asked the question, correct?
Yes.
Okay, so Josh, you broke up there. So let me just see if I can repeat your question. You can tell me if I understood it right. You went to Carnegie Mellon. Chrysler sponsored a design competition where you had to design a suspension component, which was the upright, the knuckle of some suspension on some vehicle, correct?
Right.
And one of the teams used what you called sort of an organic approach, where they define the hard points of the design and then let the computer generate the geometry in between, correct?
Exactly.
Okay, so that method is called topology optimization, and we're going to go into topology optimization in great detail. I've used topology optimization to great success on body structures and some suspension components and some transmission housings. The software, or the concept, originally was developed without what you're calling these manufacturing constraints. As these tools have become more popular in industrial applications, the publishers of these software, the people who write these softwares, have very much focused on design constraints. So can a structural member get too thin? Can you put a structural member through the driver's head? Probably not, nor through his leg or her leg. Can you make this thing from a material that you can machine? Can you make a right angle, or yes or no? Can you cast this thing? Is it actually possible to cast this thing? So the result is that they have these multidisciplinary optimization packages now, where, for example, they'll take into account things like casting. Can this part meet a design objective for castability, and also find a lightweight design given those constraints of the castability? So the castability becomes like a constraint. Or cost. Cost could be another one. This thing's going to be made out of solid gold. How much material can you really pay for, and what's the lightest weight design given that constraint of how much material can you pay for? My computer's about to run out of electricity. And then that's also this multidisciplinary thing. Not only will they combine things like manufacturability and such constraints, but they'll also put in things like aero. You need aerodynamics. How's this thing going to cut through the wind? How much energy are you going to lose driving your car down the road? They'll incorporate those components in the package as well. So that's a multidisciplinary optimization. You've got structural concerns, you've got manufacturing concerns, Maybe you've got arrow concerns, maybe you've got money concerns. And then the game is to say, how do we optimize all 4 of those, or 5 of those, or 6 of those, or n of those? And there's a whole field called multidisciplinary optimization, and they have conferences, before COVID, and they discuss ways of searching those dimensional, hyper dimensional hyperspaces, design spaces that you and I can't possibly imagine because we're just human and we really can't imagine more than 3 or 4 design variables at once, or a 3-dimensional space that includes more than 3 or 4 dimensions. Does that answer your question?
Yes, thank you.
Any other questions? Okay, good. Well, we will. I'll look forward to seeing you guys next Thursday, and we'll talk about what do we got next here. We'll talk about more of the mathematics behind these search algorithms using the gradient method. Okay, great. See you guys next week.
Thank you.
Cheers.